Hello, everybody. Welcome back. So today we are going to continue on our recommendation systems. I hope you all enjoyed your weekend. You should be on your assignment number 2 right now. And your TA just announced your assignment number 3 today. So make sure you start early. Okay. Any questions before we start? Right, let me share my screen. Okay, I think we were here. So last week we started our recommendation system lecture, and this will be a very important lecture because your final competition will be building a recommendation system. This is an application. A recommendation system is an application, but you are going to use the algorithms in this week, next week, and the entire class to help you build a recommendation system for your final project. For your assignment 3, you are going to use the algorithms this week and next week to build a recommendation system. I hope that's clear. All right, so last time we talked about different types of recommendation system, and we're going to start from our first type, which is a content-based recommendation systems. So to build a content-based recommendation system, so still remember what's a content-based recommendation system? Anybody? Okay, so it's a recommendation system that you will need to have some way to describe your data set, your items. For example, you can use metadata. It could be the color of a car, the brand of a car, the price of a car, right? Or it can be something you can learn from the data set. So it could be somewhere, not here. But these are all your item profiles. So for example, if you have a document that you want to recommend to a user, right, someone says label of the item. If you have a document that you want to, if you have an archive of many documents and you want to build a recommendation system to recommend documents, in this case, you either use metadata or labels of the item. Documents could be, let's say, what would be a good label for a document? If this is a news article, people will say this is about politics, or about entertainment or something else, right? So this is the explicit features in the database, or we can discover features in documents or items. It doesn't have to be documents. So in this case, that means we are going to have some algorithms that take the document as the input and automatically generate some tags to describe the document. And we're going to cover this today. We are going to create vector representations to represent an item. So this could be a Boolean vector, could be a numerical vector, and we are going to look at them on the next couple of slides. So if you don't know about TF-IDF, which is okay, and we are going to get into this in detail today. Once you create the item profile, you are going to profile each user as well, then you're going to base on item profiles and user profiles to make the recommendation. Okay, so item profiles. For each item, we want to be able to create an item profile. And this profile is a set of features. If you still remember, we talk about data points, right? Always look at the metrics, and you have data point 0 to data point, maybe n. And each column here would be a feature of that data point. So for example, if we are looking at movies as your data point, this column could be screenwriters, title, actor, directors, and so on. If you have text as your data point, this could be important words in each text document. But how do we convert all this profile information into a feature vector? So say features of movies are sets of actors and average ratings. Each movie has 5 actors, 2 in both movies. Average ratings will be 3 and 4. Okay, so this is just one example with 2 movies, and ratings are here. Just ignore the alpha for now. This is the unknown scaling factor, but we are going to look at them later. So in this case, we are going to use 8 feature component. Remember, each column here is a feature component, 8 feature component to represent the actors. So if you just look at this, what are the 2 columns we use to represent the actors that are shared among these 2 movies? Component 1, 2, 3, 4, 5, 6, 7, 8. Okay, so someone says 2 and 6. Great. So if you look at this, it's very simple, right? So this one is actor number 1 has a 0. Actor number 1 does not participate in movie 1. Actor number 1 did participate in movie number 2. Okay, so it has a 1. And actor number 2 participated in both movies, so you have 2 ones here, right? So you have 0, 1, 0, 1, 0, 1. So you can have a pretty long feature vector. So very simple example. So now, once we have the item profiles, how do we compare them? Remember, in built-in recommendation system, we want to be able to figure out the similarity between items. And now if you can have one feature vector to represent an item, you can just compare their feature vectors to find item similarities, right? So we can use cosine similarity. And did we cover this last time? Okay. All right, cosine similarity, it's also called cosine distance. Well, they are 2 different things, but I'll show you. So cosine distance is used in a space with dimensions, including the Euclidean space. So cosine distance is looking at angles between 2 feature vectors, okay? So let's say we have a feature vector called, did we do the skiing and hiking example? So if you look at skiing and hiking, says you want to rate your built-in recommendation system, you ask your user to rate them, okay? So user number 1 says, I like skiing, 3. I like hiking, 3, says here. User number 1. User number 2 says, I like skiing, 5. And I like skiing, 5. User number 2 is here. User number 3 says, I like skiing. I also like hiking, and here. Okay, so if you look at this, user number 1, 2, and 3, these are your data points, D1, D2, and D3. And the feature vector has 2 components, skiing and hiking, right? So what would be the value in D1? D1 would be 3, 3. D2 will be 5, 5. D3 will be 4 and 3. Okay, so there are multiple ways to measure the similarity between all these data points, right? Although I'm talking about users here, you can look at users as items. Each user right now is represented by a feature vector of a dimension 2, two-dimensional vector. And if you want to figure out similar users, which pair of users would be the most similar ones? Anybody? How do you measure similarities? We covered the Jaccard similarity, right? But very straightforward. Now you have a two-dimensional plane. You can just say, all right, here's a line. Here's a line. Here's a line, right? So someone said 1 and 3. So if you're saying 1 and 3, there's no, well, okay, so my question is, which pair of users are the most similar, right? Did I tell you how do I value this similarity? Well, I did not. So based on your answer here, I can see there are different ways you're looking at this problem, right? So someone could say the shortest distance will be the most similar because it's on two-dimensional plane. I want to find the shortest distance. Others says 1 and 2 are the most similar. So why 1 and 2? Well, if you look at their scores, 1 and 2, they both rated skiing and hiking with the same strength, right? So that means they do not have any preference between skiing and hiking, which is good. We want to be able to capture this type of similarity. And if this is the type of similarity you want to capture, we can use a similarity matrix called cosine distance. And how does cosine distance work? Instead of treating each data point as a point in the Euclidean space, we are treating them as a vector. So this is a vector for data point 1, this is a vector for data point 3, this is a vector for data point 2. And the cosine distance between two vectors is their angle. Okay, so you can see there's no 0-degree angle between 1 and 2, which means they are exactly the same if you're using cosine distance to measure their similarity. And they do have some between 1 and 3, there are still some small angles, so 1 and 3 are not exactly the same. Okay, so that's cosine distance. And cosine distance is a very common way in a very common evaluation metrics used in building the recommendation system. Also a very common similarity metrics in data science, right? So very often people would prefer cosine similarity, okay? So cosine distance or cosine similarity, you look at points thought as directions, right? Because points are now vectors. Cosine distance between 2 points is the angle that the vector to all these points make, right? Like here. It ranges from 0 to 180 degrees. So you can have two vectors of the same direction. Then you have 0 degree. You have two vectors of completely different direction. That's 180 degree. Can you have more than 180? Well, you can't. Because if you are here, we are not really measuring this, we are measuring this. Okay, so 180 is the maximum you can get. So how do we compute the angle? This is high school math. You compute the cosine of the angle between two vectors, then apply arc cosine to translate them back to 1 to 100 degrees. That's your cosine distance. Okay, so I'm not going to get into this too much, but let's just look at the equation here. So the similarity is cosine theta, which is if we have two vectors, it's the dot product between two vectors divided by their distance from the origin point. Okay, so where is the example? So this is the dot product, this is the Euclidean distance, this is this. But I think this example might be clearer. Say you have two data points. Okay, so well, instead of calling them y, x, and y, we can call them D1 and D2. Because sometimes when people look at x and y, it feels like you have x exit and y exit, right? D1, D2 will just tell you these are just data points. So their dot product is this. Why do we have 1 times 2? 1 and 2, right? 2 times 1, 2 and 1. Minus 1 times 1 minus 1 times 1. So this is your dot product. You multiply the corresponding component and add them up. The Euclidean distance of the two vectors is also super easy to calculate. It looks like this, right? So 1, 2 minus 1. This is 1, 2 minus 1. And you do the same thing for y. It's again 2 square plus 1 square plus 1 square, and take the square root. You have square root 6. So the cosine of angle from x to y would be 3 divided by this, or 1 over 2. And if you apply our cosine to 1 over 2, that will give you 60 degrees. And this is the cosine distance between x and y. Okay, so distance is in degrees. So if we look at our previous example, this is our movie item profile, movie 1 and movie 2. Let's do a dot product. You will be able to generate this, right? Dot product give you 0, 1, 0, 0, 0, 1, 0, 0, 12 alpha square. The distance from the origin point is do the same, and you have these two numbers. Then you can calculate the cosine of angles between these two vectors as this. Okay, so will this take us to the question, what exactly is alpha? So if you look at this final answer here, you can see that alpha plays a very important role, right? So if we have alpha 0, compare alpha as 1, compared to have alpha as 0.001, this answer will be very different. So how do we choose alpha, and why alpha is important? Well, this is because the reason why we need alpha is because if you look at all these components, every components here are having the same type, right? Data type. They can either be 1 or 0. But for this component, it can be in the range of 1 to 5, for example. And let's say, just make an extreme example. Let's say you have 8 components for your actors, and your rating is not from 1 to 5. Your rating is from 1 to 100. Okay, so what does this mean then? This means this alpha, without using alpha, this component can be really large compared to all other components, right? This can be 100. And this 100, if you do a dot product, you have 100 times 100, you have what? 10 to the power of 4. And that's a really large number compared to all the dot product from here, right? So what would be the maximum summation you can get from doing dot product from here? You will have a 1, 1, 1, 1, 1, 1, 1, 1 everywhere, right? That's the largest number you can get. So that would be 8 plus 10 to the power of 4, right? Where does this come from? This comes from this review ratings, and we are using an extreme example, saying the review can be 100, okay? So if you look at this review actually dominate your dot product, right? So we don't really want this. In this case, we want to have an alpha, maybe 1 over 1,000 to scale this review into what? 10, right? So you have A plus 10, that's more reasonable. Okay, but still this one component almost, well, in this case, have a larger weight than all other 8 components. So maybe you don't want to use 1,000, you want to use 10,000, 1 over 10,000 to scale your ratings. So how do we actually find this alpha? Well, every application can be different. So you will take some small examples, take 2 items and compare them, trying to see what would be the alpha that would make sense, right? So in this case, we will probably use 10,000 to make sense, for it to make sense. All right, so we talk about these item profiles and how do we compare 2 item profiles using cosine similarity. And that example was for movies, for which we can use actors and ratings to help us generate that feature vector. What if we don't have those information? Well, the next topic I'm going to tell you is using textual content to build that feature vector. So here we want to build item profiles based on text content. And there's a lot of research working on text content for a recommendation system. The application could be recommend items like web pages, books, movies based on some associated textual content, or it could be descriptions, user reviews as well. We can treat this as a information retrieval problem and identify things or to documents that are about similar things. Okay, we want to be able to pick important features of documents, and we want to be able to identify significant words in the document to represent them. So let me just give you one example. Let's say we have many documents here. And the user comes in, user has some profile. Say user has read 2 documents from your database. And your goal is to find the documents similar to all the documents that the user has read and return that or recommend that to the user. Okay, so can we use that similarity, finding similar documents, Shingo approach from last week to solve this problem? Can we? Anybody? So we want to find similar documents, right? Convert them into Shingos, compare Shingos of a document, and then find them. All right, so we have an answer, say we can, but okay, the right answer is we cannot. So why not? Anyone?
Is it because similar items does not imply frequent items? They're not kind of the same thing?
No. So remember when we talk about similar, you can define similar, the words, you can define similarity in many different ways, right? So what type of similarity were we looking at or were we looking for in that finding similar document lecture using Shingos and OSH and MinHash?
Sets instead of strings.
Right, we are looking at sets, right? So how do we generate all these feature sets? Those are Shingos. And when we find Shingos, our goal is to find 2 sets of Shingos that are similar, right? So we care more about the lexicographic similarity, which is very useful to find 2 documents that are near identical or to identify plagiarism cases, right? But think about recommendation system. If someone already read that article, do you want to find another article that is nearly identical to the document that the user read and recommended to the user? Probably not, right? What you really want to do is to identify the topics that the user has read and take that topic to find documents that have similar topic, right? So for example, if the user read documents about well, let's say news about Los Angeles Lakers, then you know, okay, the user might be interested in basketball, NBA, or sports, right? Then you will be able to find documents that are about all these topics and recommend it to the user. So just don't be confused about similarity. When we talk about similarity, there are different ways to define them for different applications and also for different algorithms as well. So the algorithm that we are going to discuss right now is called TF-IDF. You should have already read this for your chapter 1. TF-IDF is a very, very, very commonly used algorithm to measure the importance of words in a document. But what do we mean by importance of a word? TF-IDF score can tell you the words that have a high score from a document tells you the topics of a document given a large repository. Okay, so we want to be able to classify documents as being about similar topics or themes. And we want to start by finding significant words in those documents. These are not the frequent words. These are usually called the stop words, the, and It's not rare words. We don't want to use rare words. We want to concentrate on useful words in just a few documents. I'm going to tell you what does this mean. So useful words usually means it appear many, many times. So that's this component in the TF-IDF. In a few document means this word appear only in a few document in your repository. So if that appear in one document, that is rare and important. So we want it. This is the IDF component. So words with the highest TF-IDF scores are often the terms that best characterize the topic of a document. And when we start to construct an item profile for a recommendation system for documents, all these terms that you can identify will be features. And your documents are your items. Okay, we're going to look at a complete example on how to do this next. Okay, so I'm thinking, should we go? Okay, let's use the whiteboard first. All right, so we're going to work on one example about text mining. It's a very cool example. Say you are you have a large document repository, and it is from New York Times. Your goal is to be able to separate the document into a few categories. So from New York Times, you have 1 million documents. Naturally, if you have some experts to look at all these New York Times articles, you might be able to split them into politics, entertainment, sports, and finance. Okay, and how does a human do this? Well, if you have all this predefined category, you tell a human this will be the things that you are looking for. A human would have some built-in keywords filter, right? So for example, the human would say, all right, politics. This is New York Times for the US, so you probably have Democrats. You have Republican. What else? Election, campaign, and all these words, right? So if that human expert find all these words, it will just directly put it into the politics section. For entertainment, you probably have Hollywood. I'm making this up, so just bear with me. Hollywood and what else? Rock and roll, movie, TV, Netflix, maybe some award, sports, NBA, and MLB, NHL, football, finance, probably have stock, bonds, GME. What is GME?
GameStop.
Yes. I hope you're all holding. Okay, that's a joke. All right, so you have all these words for different categories in the newspaper archive, okay? And if a human look at all these words, it will automatically, the human will be able to sort all these articles into one of the categories, which is cool. And we can look at these keywords as topic words, right? So we can say these are topic words for entertainment, these are topic words for sports, these are topic words for finance, these are topic words for politics. Good. So TF-IDF is an algorithm that will be able to help you to generate all these topic words, but it will not tell you this is for politics, this is for entertainment, this is for sports, and this is for finance, okay? It probably will not have exactly these 4 groups, but it will have some groups and some keywords, which is cool. So let's look at all these keywords and think about why these are important words. So if you look at politics, articles in the politics section, you probably see these words very often, right? And these words are important or topic words for politics because they appear very frequently here, but not very frequently in any of these categories, okay? That's why they are the topic words. And if you look at this, they appear very frequently here, but not here, and not here. Sports, they appear very frequently within this group, but not here, not here, not here. So when I say groups, I mean, you probably have, so you have a total number of 1 million document, maybe you have 200K here, 250K here, you have 300K here, you have the rest of the K here, okay? So that's the number of documents you have in each category. And when you are looking at the topic words, so based on my description of the topic words, think about this. When your algorithm wants to decide if this word is a topic words for a certain document or for a certain category of the document, what would be the input of the document? Sorry, the input for the algorithm. The input will be the document itself, right? Because this word has to appear many, many times in this document. Also, all the documents in other categories or not in this document, right? So that means the word Democrats should not appear very often here, here, and here. So when we build TF-IDF feature vectors to describe documents, your input always needs to consider the entire document repository as a whole, or your result will be different. Let's look at one example. So say you still have 1 million documents, but this 1 million documents are not randomly sampled from New York Times. They are sampled from one category of New York Times. And let's take this category. Which category should we do? Sports. Sports category. Now you have 1 million document. And if I tell you to split the sport category into different groups, what do you think would be important words for each group? Well, this time you probably have NBA here. You have MLB in a different group, right? You have NHL, you have what? MLS. Okay, so this will be basketball. This will be for baseball. This will be for football. This will be for soccer. Okay, then you probably have other keywords: Lakers, Galaxy, Ram, Dodgers, and all that. So what does this mean then? This means the word NBA, basketball, Lakers appear many times in this document or this sets of documents that's about basketball. All these words here appear many times here, but not here, not here, not here, right? This appear many times here, but not here, not here, not here. This appear many times here, but not here, not here, not here. This appear many times here, but not here, not here, not here. So you can see the keywords or the topic words for a document or for a document set has changed. These are all the same documents from the sports categories, but originally the entire category share all these keywords. All right, now you start to have all these, you can call them, if you look at them as a hierarchy, this will be the first set of keywords. This will be the second set. You start to have basketball, Lakers, baseball, Dodgers, and so on, right? So this is because when we look at the document the repository as a whole to be able to find TF-IDFs, you are now comparing all other documents within the sports category. One extreme example would be originally, there could be a keyword here, it's called sports, right? If you have a news article that contains the keyword sports, that might be in the sports category. So this is a good topic word. However, when every document is about sport, this sport, the keyword sports, will not be that important. But it's like the milk example in your association rule, discovery lecture, sports will be everywhere for every category. And it does not provide us any helpful meanings to separate documents from one category to the other. Okay, so this is the basic idea of TF-IDF, and we can go back to the slides. Okay, all right, TF-IDF. So let's say this Fij. So here I'm going to show you how to calculate it. So Fij is the frequency of term I or word I. So term and word are the same thing here. In document J, term frequency TFIJ, remember always a word and a document, is the frequency of that word in the document divided by the maximum frequency of any word in the document. Okay, so that means it's normalized. And most frequent items or most frequent words will have a TF equal to 1. We're going to look at one example on the next slide. So this is your TF. For your IDF, your inverse document frequency is the log of n over ni. So n here is the total number of documents in the repository. Remember, well, on the whiteboard, I told you when you want to calculate TF-IDFs, you need to consider the entire document. Sorry, entire repository of documents. So n is the total number of documents, and I is the number of documents that contains the term I. So it's here. H take the log. As far as why are we taking the log? Well, it's very common in taking logs in either data science or machine learning. So for example, we will see that log maximum likelihood, you take log on a function. But unfortunately for TF-IDF, no one has ever been able to prove that the log we are using here is the best way to do it and providing a good foundation, theoretical foundation for the log. It's a heuristic, but people use it and it's very practical. That means after you take the log, things start working. So no one is able to explain this, as far as I know. All right, so TF-IDF score for a word, Wij, is the TF times IDF. So again, look at it here. What does this mean? This is the TF-IDF score for a certain word, I, in a document J, which include the term frequency. This is the normalized frequency of that word in that document. And this is the IDF. This is the popularity of that words in every document, measured by the word in every document in the repository, right? So you only have I, you don't have J here. So item profile for a document would be a set of words with the highest TF-IDF scores along with their score, but we're going to look at this later, so don't worry. Let's look at one example on calculating TF-IDF scores. That's here. Suppose your repository has this number of documents. Suppose your word W appear in this number of documents. Okay, this is for calculating your IDF. Right, if you look at here, this is the number of documents in the repository. This is the word I, right? How many documents contain word I? If you take a log on this, you have a number of 10. So IDF is 10. Consider a document J in which word W appear 20 times. Remember, TF-IDF concerns a document and a word, right? So you have to have a document. So this is the maximum number of times any words appear in that document J, so TF will be 1, okay? That means W is the most frequent word, so it has a very important TF score because it's 1. TF-IDF score will be 1 times 10, that will be equal to 10. Great. Let's look at document K and the same word W. In this case, do we need to recalculate TF and IDF, or can we reuse them? Because you're looking at the same word. You don't have to recalculate the IDF because IDF concerns only the word, so you can reuse that 10. But for your TF, that's the term frequency. Here it tells you that word W appear in K just once, so I have a 1. And the maximum number of occurrence of any word in K is 20. So TF will be 1 over 20, right? So look at this. This is 1 because it's the most frequent word in that document. This only appear once, and the most frequent word appear 20 times. So it's 1 over 20. And the TF-IDF score for W in K will be 1 over 20 times your 10. That will be 1 over 2. So very easy, but let's look at one example before we take a break. Say now W appears in all the documents, okay? So instead of 2 to the power of 10, you have 2 to the power of 20. So this is 20, this is log 1, this becomes 0. What would be the TF-IDF score for W in J? That would be 1 times 0 equal to 0, right? So this tells you, although TF score for W in J is very high because it's the most frequent word in J, but it appears in every document. So IDF is 0, and the score, TF-IDF score, becomes 0. So this is a perfect case for our sports example, right? So say you are looking at the repository of newspaper articles from the sports section in New York Times. It has 1 million documents. Almost all news articles in this category contains the word sports. So the IDF score for that word sports will be very low. although the turn frequency for documents for the sports can be high, but eventually the TF-IDF will be very low because you have a low IDF. Okay, so punish the popular words. All right, 6:50. Let's take a 10 minutes break. Come back at 7. If you have any questions, make sure you leave a comment in the chat and I'll answer them when I come back. Thank you. All right, I'm back. Let's continue. All right, we were talking about TF-IDF and the scores. Let's look at here. So in general, to make recommendations based on document features, we will be able to suggest articles, pages, blogs, social media posts that a user might want to see. But it's very difficult to classify them by topic. So in practice, what we can do is to identify words that characterize the topic of a document given a huge repository of the document. Okay, that's a very important part. Don't ever forget that. You cannot just take one document and generate TF-IDF scores for each word. You need a repository of the document. Because remember, like in that sports example, the topic word of a document can change depends on your repository, right? If your repository is all about sports, then an article about the Lakers will not have a TF-IDF words sports. It might have TF-IDF words, maybe NBA, Lakers, Los Angeles, and so on. However, if your repository contains all documents or news articles about Los Angeles Lakers, then NBA, Lakers, what else? Los Angeles will not be important words for that document. Okay, so always consider the entire repository. The step that you have to do would be to eliminate stop words for the remaining words, calculate your TF-IDF scores like we did from the last slides. The words with the highest TF-IDF scores would be the one that you can use to characterize the documents. All right, so now you know how to generate TF-IDF scores. Then what do you do next? Well, let me show you on the whiteboard. Okay, so this is the entire process of TF-IDF, which will be on your quizzes and exams. So just pay attention here. Let's say you have a repository. Well, not just because quizzes and exams, this is an important topic. You have a repository of 1 million documents, and we want to be able to generate feature vectors to represent your documents, right? Assuming you don't have other metadata, you want to be able to learn these features from the document content itself. So what do you do? Well, you start by reading the first document, you read the file, So you take the first document, you parse it. What will be the result after you parse it? You have individual words. Then you look at a stop words list. So this type of list is very common. You can find them online. Many repositories contain them. It's like a dictionary. So this contains words like the, you, I, and so on. Okay. So you look at the stop words document, you say, oh, I don't want all the stop words because they are not meaningful. You just remove them. For the remaining words, what you can do is you are going to count its term frequency. Okay. So to count the term frequency, what you will need to do, let's say these are all the remaining words. you count the frequency first. So you say, all right, this word number 1, 2, 3. The first word appeared 50 times, second word appeared 66 times, 71 times, and so on. Okay. Then you identify the words that have the maximum term frequency, assuming it's 61. So this is max in the document. Then you can calculate term frequency by taking the 50 divided by 61, 66 divided by 71, 71 divided by 71, and so on. Great, you have the term frequency for each word in this document, X. Okay, great. What do you do next? Well, you process the next document and you generate all this TF for the second document and so on. Okay. All right, so now you have processed all the document. What is your result? You have all the documents that you processed, and you have the TF score for all the words for every document. This is document 0, document 1, document 2 to document 1 million. Are we good so far? Calculating TF, very easy, right? So now what do you want to calculate? Well, you want to calculate the IDF. How do you calculate IDF? You take this word and you look at all other documents to see if they contain this word, and you count how many documents contain these words, and you say, all right, 5 documents. And we know that the entire repository has 1 million documents, so your IDF is this. You can use log 2, log 10, doesn't really matter much, just be consistent, okay? For the second word, you do the same thing. You count how many documents contain this word, and you come back and you say, all right, 1,000, and so on. Then you move on to the second document. Remember, here this list is unique, right? These are unique words. You just already counted the term frequency for each unique words. But could these words be the same as this word? Yeah. If the same word appear in 2 documents, they can be the same, right? Across document, they don't have to be unique. So, for example, this word can be MBA. This word can be MBA as well. So for the word MBA, you already calculate the IDF. You can just take that IDF and you say it's log 1 million over 5. So you don't have to do this. You don't have to ask if any or other documents contain MBA anymore. Right, so for new words that do not appear in D0, you have to ask if all other documents contain them, and you generate the IDF score. Let's say this one has 1 million. It's a very popular word, so this one has a IDF of 0. Okay, great. Once you will be able to do this for everything, you will be able to calculate the TF IDF for each word for each document equal to this, right? You just take TF times IDF. So this is multiply. And you do this, then you have the TF IDF score. Are we good so far? So for the 0 to the 1 million, now you have TF IDF words. It looks like this. You have a word, say MBA, and I'll just use some simple key value pair expression. You say I have MBA and the score is 3.5. I have acres. The score is 4.5 and so on. Second one says I have the words. What? Let's make more examples. Lakers and basketball 2.9 and Kobe 1.8. Okay. Second one says sports. 3.8. Dodgers. 3.2. Baseball. 2.9. The third one says Los Angeles. That's not a very good example because Los Angeles might not be a word, right? Say finance. 2.9. 3.9. Stock. 3.8. Maybe this one also has MBA for some reason. Okay. 3.7. All right. So how do you create feature vector then? You look at all these documents in their TF-IDF words. There are multiple ways you can create feature vectors. First one, you can pick top keywords. So let's say we pick top 2. Then for your D0, the matrix become this top, okay, equal to 2. D0, you have MBA, and oh no. What's the most important words in D0? Lakers, right? Lakers has a TF-IDF score of 4.5 and MBA 3.5. For D1, what do you have? What would be the top words? So the question, there's a question why the TF-IDF words of the two MBA are not the same. Where do we have two MBA? Oh, okay. So one is here and the other one here. So always remember TF-IDF score contain two components, TF and IDF. IDF is the same across all the documents, but the TF, the term frequency, is not the same, right? The term frequency will be different in this document and in this document. It depends how many times MBA appear in this document and MBA appear in this document and the maximum, the most frequent words in that document. So these two numbers can be different. Okay, so now we have D0, D1, and D2. So for D1, what will be the top two words? Dodgers and sports. So Dodgers, let's do sports first because it has a higher score. Sports and Dodgers. So sports 3.2. Sorry, sports 3.8, Dodgers 3.2. And if you look at here, D1 does not have Lakers, 0. Does not have NBA, 0. D0 does not have sports, does not have Dodgers, 0, 0. Okay. All right, finance, top 2. Oh, bad example. Let's make this 3.5 so that your top 2 will have finance and MBA. Okay, so you already have MBA here. You just put MBA 3.7 and finance 3.9, and everybody else are zeros. Okay, so great. This is a way to generate your feature vector. So pick top k equal to 2. A second method, very similar to this one, is you pick top k, let's say k equal to 2, but instead of using the TF-IDF values here, you just use 1 or 0, right? So 1 means D0. D0 contains Lakers. 0 means D0 does not contain all the other words. And this will be 0, 0, 1, 1, 0, 0, 1, 0, 0, 1. So it depends on your application. Maybe one, it make more sense than the other. But if you are using 0 and 1, you can use Jaccard similarity, right? Remember, Jaccard similarity is measuring the distance between sets. And if you are using TF-IDF numbers, you can use cosine similarity. similarity. So pick the top K is one way to do it, or the other things that you can do is, second, pick a threshold. You can say, I only want the TF-IDF words with TF-IDF value larger than 3. So if you do that, all the TF-IDF words that you can use to describe the 0 will be what? NBA, Lakers, that's it. For D1 could be sports, Dodgers, and that's it. For D3, it will be finance, stock, and NBA, right? So this gives you different sizes of keywords for each document. And then you do the same thing to generate the feature vector, then you can compare them. All right, so this is everything you need to know about creating a feature vector to represent a document. Let's go back to the slides. So I already explained this. Oh. I already explained this. You take all these TF-IDF words as features of the documents. You can take n words with highest TF-IDF score, pick the same n for all the documents, or it can be a fixed percentage, or like what we did on the whiteboard, you use TF-IDF score threshold. You can also make this above a given threshold to be a part of the feature. Then your documents represented by a set of words, and we expect this set of words to be able to express topics or main ideas of that document. Then we can measure the similarity of the two documents using cosine distance or Jaccard distance. So think about cosine distance. We saw this today. We did this today, right? Movies, cosine distance, dot product divided by the length. With document similarity using Jaccard distance, we are going to think this sets of high TF-IDF words as a vector, right? Because it's a cosine distance. With one component for each possible words, vector can be 1 if the word is in the set of the document, 0 if it is not. Or you can use the TF-IDF scores instead of 0 and 1, right? We did this on the whiteboard. So between two documents, only a finite number of words among their two sets, right? They would only share a finite number of words. Like in our example, only document 0 and 2 share 1 word. Almost all components will be 0 that do not affect the dot product. Look at here. If you have many zeros, this will be a small number. The dot product will be the size of the intersections of the two sets of words. The length of the vector will be the square root of the number of words in each set, right? Because now your vectors are either 0 or 1. Then you can calculate the cosine distance. So this is just help you how to think or how to conceptualize this cosine distance measurement can be applied to your TF-IDF vector in the case that your vector has 1 and 0s. If your vector has scores, TF-IDF scores, it will be pretty much like what we did in the skiing and hiking example. All right, so we are 7:20 now, and it's quiz time. So please turn on your camera. If you have any questions, please ask. And just like we said on the Blackboard, you can have until 8 p.m. to submit today. So you have 10 more minutes. It's very important, so I just say it 3 times. You can have until 8 p.m., 10 more minutes, 8 p.m., 10 more minutes, 8 p.m., 10 more minutes. All right, so since you are going to have more time to work on the quiz, I am going to quickly explain your quiz on the screen. All right, so question number 1, very easy, but you need to read the textbook to know what's the Jaccard-Beck similarity, or if you follow Piazza, someone asked this question. 2 shingles for this string, also very easy. And this is to ask, the third question, this is to ask you to write down the signature for this matrix in one pass, exactly like what we did on the slides, okay? All right. Question number 4, it's about this very cool graph. So I want you to generate this function from S and R and B, and you need to explain what's S, what's R, and what's B, and you have to derive this. Then you have to talk about how B and R would change the curve and why do we care about them, right? In terms of false positives and false negatives. Okay. Then the last question is the overall approach question. I think we did this on the whiteboard. So given a repository of 1 million documents, please describe how you would use this 5 shingle to characterize each of them. Right? You have to generate feature vector for each document using these 5 shingles. So how do you do that? Then once you generate the 5 shingles, you will need to use min hash and LSH to find most similar documents to a new document that is not in the repository. So how do you do that? Okay. I know on your question 3, you are going to show how you would generate the min hash. But here you just need to provide some short description on why are you doing min hash, what exactly is min hash, and what exactly is LSH. Okay, so just a brief note. The goal for LSH is to prevent you from comparing the new documents to every document in the repository, right? So your process of finding 2 similar documents by comparing the band, remember LSH are going to looking for identical bands. The process of finding identical bands should not be comparing every signature. Remember what we did on the whiteboard with the hash function? So that's the answer here. All right, enjoy your quiz. I'll see you on Wednesday. Make sure you do all your homework and do your readings, come to your office hours, and you'll be okay. Do we have our TA here?
Yeah, I'm here.
Okay. All right. Thank you, guys.
Time's is almost up. Please remember to upload it by 8. All right, guys, time's up. End the sessions.